Okay, welcome back. It's the final week of this class basically, and we are going to learn our final set of things. Last week we did a bunch of stuff. We introduced finite state machines. We introduced regular grammars. We introduced regular expressions. And we introduced non-deterministic finite automata, and we presented an algorithm that shows that non-deterministic finite automata and deterministic finite automata are equivalent to each other. Okay, we mentioned several times that in fact these three different constructs all seem to be describing in different ways the exact same thing. And that is true. And we're going to prove that now. So here, the vocab I think is important. We have, let's go in chronological order. We, we introduced these finite state automata, these finite state machines, and we showed how a finite state machine can either accept or reject a certain particular string. And the set of all strings that a particular finite state machine accepts is called a language, and we say that that machine recognizes that language. That's the verb we use. We also explained regular grammars, and we explained how a regular grammar generates a string, and the set of all strings that a particular regular grammar generates is called a language. And this is not standard because obviously it's going to turn out to not matter, but our textbook, Gossett, defines a regular language as a language generated by a regular grammar. Okay, so for the moment, for us, that's what a regular language is. A regular grammar generates a regular language. And then finally we have these regular expressions, so regular expressions are this sort of extra vocabulary with all of the characters of your target language, the alphabet, plus some extra characters like the star and the vertical bar, the alternator or something like that it's called. I can't even remember. I don't think I explained it last week, but I just was looking it up on my phone. People call it the, man, I don't remember. It doesn't really matter. All right, great video. Woo! Anyway, it doesn't matter. But now it matters, because I'm angry. Anyway, okay. Never mind. Alternation. Okay, so concatenation, alternation, and Kleene star. So that's called an alternator, I guess. You can just call it the or symbol, the vertical line, the pipe. Okay, so anyway, with what is a regular expression? It has a precise syntax, and we showed in one of the videos last week that a regular expression matches a certain string, and then the set of all strings that a regular expression matches is also a language. Okay, there doesn't seem to be any total consensus on what to call this. Gossett says generate, but other people simply define the value of a regular expression to be equal to the set of strings that match it. So then maybe the correct verb would be a regular expression just is a language in the sense that, yeah, okay, because then that's the value of any particular regular expression is the set of strings, that it matches. Okay, anyway, here we go. What our claim is that, okay, by definition, a regular language is the language that a regular grammar generates. What we want to argue is that a finite state automaton also recognizes a regular language. That every language recognized by a finite state machine is regular, and that for every regular language we can recognize it with a finite state machine. And that every regular expression generates a language, and that that language is regular, and also that given any regular language, there is a regular expression which matches all and only the strings of that language. Okay, so in other words, this is just a long-winded way of saying that all three of these are equivalent to each other. Okay, so to complete this proof, what we need to do is sort of show that regular languages are what we're talking about, just in three different ways. Okay, and here's the outline of how we're going to do this over a sequence of several videos. The first stage is the easiest. We are going to show, the first thing we're going to do is we are going to show, I think this is the first thing we are going to do, yeah. The first thing we're going to do is we're going to show that a deterministic finite automaton can be turned into a regular grammar. So I'll just say DFA to, well, sorry, let's do, or maybe I'll just do it like this. So here, I'll draw the arrow, but now I'll just list the things I'm going to do. I'm going to show that any deterministic finite automaton can be converted into a regular grammar. And okay, what I mean by that, of course, is that given a particular DFA, I can create a regular grammar, and that regular grammar is going to generate precisely the same strings that that DFA accepts. Okay, then we are going to take an arbitrary regular grammar and we are going to algorithmically convert it into an NFA. And by that I mean, given any arbitrary regular grammar, we will show how we can construct an NFA which accepts all and only the strings that that regular grammar generates. And this suffices because of previous work that we've already done, that's why I put a check mark here, showing that the reason why we can be vague when we just say finite state machine is that NFAs and DFAs are in fact equivalent to each other. And there exists an algorithm which we will now sort of bury under the hood that says that any NFA can be converted, if you wish, into a DFA. And so we will consider this equivalence having been shown. So this is the second thing we're going to do. If we can convert the regular grammar into an NFA, then we could also convert that regular grammar into a DFA. Okay, then in a separate video, which I think is going to be harder, we are going to show the equivalence of finite state machines with regular expressions. And I guess it doesn't matter which order we're going to do it in, but I do have a plan somewhere. I can't remember which one I'm going to do first. I think, yeah, I can't remember. But we are going to show that every DFA can be converted into a regular expression. So DFA to regular expression. And then we're going to show, hope this is right, then we're going to show, one second, I guess we're going to go regular expression to NFA. Maybe I should do this properly. We're going to do regular expression to NFA. So we're going to show how we could construct an NFA given any regular expression, and then NFA will accept all and only the strings of that regular expression generates. And finally, we will show, given any DFA, that, I think that's what we're going to do, that for any, no, I guess we're just going to do it all at the level of NFAs. For any NFA, why is that a good idea? Okay, that there is a regular expression that matches it. Okay, so in other words, we're going to do these two, and and owing to the equivalence of NFAs and DFAs, then this just completes the job. Okay, good. I will say that the first two of these are very simple, almost trivial, that don't need to be almost mentioned because they're so sort of obvious what to do. And then the next two are more complicated and in fact have lots of small subtleties. And actually, if you follow Gosset's algorithm exactly, it's wrong. So, okay, let's go. And these are algorithms, so I will say that the point of these algorithms is, well, to prove the theorem, but also in practice, we would like to be able to convert between these things. For example, maybe we want to use regular expressions, and, well, for example, I'll give you the big example. Suppose you want to know that if two regular expressions are equivalent to each other. Well, in fact, there is an algorithm for this, but it is extremely difficult. It is, in fact, like NP something something something. I won't say anything else because I don't know what I'm talking about, but you can do it. It takes like exponential time and space and all the terrible things that you don't want from an algorithm. But the algorithm does exist. How do I show that two regular expressions are equivalent? And by that I mean that they match exactly the same set of strings. Well, you convert this regular expression to an NFA, each of them to an NFA. Then you convert each of those NFAs to DFAs. Then you convert those DFAs into some minimal DFA according to some minimization process. And then there exists a separate algorithm, which I don't even know, to tell whether two DFAs in this sort of minimized state are in fact isomorphic. And if they are, then they accept all and only the same strings, and so those regular expressions were equivalent. Okay, why am I mentioning this? Just because, like, these are supposed to be algorithms, so you're not supposed to have to be smart. So I would like you to resist the temptation to just kind of like do what we have been doing this entire unit so far, which is when faced with a finite state machine, just kind of look at it and just be like, oh, this is just, and then just write the regular expression. Though that might be easier in certain cases. When the DFA gets really hard, and we saw some examples of this already, it can be quite difficult to figure out what exactly those strings are. So the benefit of the algorithm is, you're not supposed to have to be smart to be able to execute it once we understand the algorithm and verify that it's true. Okay, so I'm going to go through the steps in a kind of a careful, methodical manner. All right, we begin. We're going to show that we're going to do 1 and 2 right now in this video, and then we're going to pause for me to review my notes on the others. Got some kind of eraser problems here. All right. And I'm taking these examples more or less straight from Gossett. He does a fine job here, although I object to 1 or 2 of his small issues. So, okay, let's go. Here we're going to do what I hope I called number 1. We're going to go from a DFA to a regular grammar. And I don't think anything is gained by somehow doing this in general. So we're just going to give a particular example, and we're going to sort of explain all the steps of what should we do. Okay, so suppose you have a DFA, and suppose it looks like this. The normal person would just kind of draw their DFA. Here's Y, here's Z, and okay, so we have 3 states, X, Y, and Z. This is A, B, and A, and also AB. Okay, so this is the DFA because, well, there's just no non-determinism. We have no lambda transition states. We have for every state exactly 2 transition rules for what to do upon each input. We have 2 accept states, X and Z. So formally, this DFA is like a tuple. It's a 5-tuple. It's a 5-tuple consisting of the set of states, and the alphabet, and the transition function, and the start state, which in this case is X, and a set of accept states. Well, maybe I'll just write it like this, and a set of accept states. Where here, of course, the set of states is X, Y, Z. The alphabet is AB, and the set of accept states are X and Z. Okay, so how can we convert this DFA into a regular grammar? Okay, well, you just basically do it. The language we even use for these grammars and these states are sort of almost exactly the same, so this shouldn't surprise anyone, right? What's a grammar? A grammar is going to be, okay, so this grammar G, I don't remember exactly how this works, but there are, let's see, well, I don't remember. I bet it's like 4 or 5 things. It's some kind of set of terminal symbols, some set of non-terminal symbols, some production rules, and maybe something else too. Yeah. So prepared here. Blah blah and blah blah. Yeah, that's all right. Oh, and then I have to specify the start symbol. Okay. So, and instead of production rules. Okay, yeah. So it's a 4 tuple or a quadruple, and there's a start state and there's a set of production rules. Okay. So you have fully explained the grammar when you have given the set of terminals, the set of non-terminals, the start symbol, and the production rules. Okay, but of course, how are we going to do this? Well, we are going to take, so we are going to set this set of terminal symbols to be, I'll maybe put like subscript G to indicate that I'm defining the sigma of this grammar. Well, of course, it should just be the alphabet of the finite state machine. So we're going to set this to be sigma, and I'll call it like, I'll call it FSA just for the finite state automaton. In other words, take the alphabet of the finite state automaton, which in this case is just AB, and set the set of terminal symbols to be that same set. Except for the fact that we might also need in our set of terminal symbols for our regular grammar, we might need lambda to refer to the null string. So okay, I made a big deal about this last week, so I won't go into this all again. I think Gossett is confused about this a little bit, so that's, if you want the technical answer, there it is. Okay, and then what should I set my delta to be? Well, basically what we're going to do is we're going to create a non-terminal symbol to represent every one of the states. So basically set delta to just be the S from the finite state machine. Or, this is a little bit vague, but I think everyone gets the idea, right? For every single state in the machine, create a corresponding non-terminal symbol which represents that state. Okay, and finally, what should I set S, the start symbol, to be? So I'll just keep putting these subscripts in here just for clarity. Let's set the start symbol of my grammar to be, whatever the start state is. Maybe this is more clear. So yeah, and this kind of says, right, because every DFA is really like a set of states, an alphabet, a transition function, a start state, and a set of accept states. And so here the start state is X. So set the basically set the start symbol of your regular grammar to be the non-terminal symbol that corresponds with the start state of your NFA. Ugh, this video sucks so far. Woo! Okay, good. So where's all the work? All the work is happening, of course, in the transition function. So how can I define this is the transition function. This is the set of production rules. Okay, so what I'm now going to do is algorithmically explain, and as I explain, I will justify why this algorithm just proves itself. I will explain how I can convert each transition, each rule of the transition function, or each ordered triple of the transition function. Each piece of the transition function has a corresponding production rule in the grammar. And well, here it is. If I'm in, let's just begin. If I'm in state X and I read a B, I'm supposed to go back to state X. So now I just add a regular grammar production rule which says that X goes to BX. In other words, if you're in state X, then just write a B and go back to state X, is all this really says. What happens if you're in state X in the machine and you read an A? Well, then you just go to state Y. Well, then if I am if my cursor, so to speak, is on the non-terminal symbol X, which corresponds to the state X in my machine, then I should write an A and go to state Y. Okay, and then the last thing to recognize is that this state X is itself an accept state. And since it's an accept state, we need to be able to generate the null string. The null string is certainly a string of this of the language that this machine recognizes. So we just create a rule that says X goes to lambda. Alright, and now we just keep doing this, right? If I'm in Y and I read an A, I'm supposed to go to Z. So Y goes to A, Z. In other words, if you create a rule in your regular grammar, which is okay. If you are in Y and you read a B, you're supposed to go to state X. So now I created a rule that non-terminal symbol Y can be replaced with BX. And then I have 3 more rules. That Z goes to AZ, that Z goes to BZ, and that Z goes to lambda. And I think there's just nothing more to say. For every single possible path through this finite state machine, through this DFA, leading to X or Z, there's a corresponding set of rules that we could follow that derives that string. And if, I guess, the converse is that if it is possible to generate a string from this language, then from this grammar, then there's a path through, then you have to have some particular derivation of that string, and each step in that derivation is an application of one of these production rules, and each one of these production rules has an exact analog here in the transition function showing that that same string must be accepted by the DFA. And so this satisfies all the rules of a regular grammar, and it just works. And okay, perhaps you want to make that argument more formal, but I am not going to. Okay, good. 1 down, 3 to go. I will erase this now. Whew. And we will do the other direction, and then we will stop. Oh, okay, good. This might be kind of short. Okay, and we're going to do 2 examples. These are just Gossett's examples. So suppose we have a particular grammar. Okay, so we're going to now do regular grammar to NFA. Okay, let's go. Oh man, I shouldn't have erased all this. Well, never mind. So suppose I have a regular grammar. What is this regular grammar? It's a tuple of, I should be able to do this now, sigma and delta, and there's a start symbol, and there's a set of production rules. And so let me explain this grammar carefully. In this case, sigma is A, B, lambda. I believe that lambda should be a terminal symbol of every regular grammar. Delta is SX. Okay, the start symbol in this case just is S, so whatever. And, sure. And, now we have our set of production rules. Here they are. There are 4 of them. There's one that says S goes to lambda. There's one that says S goes to A, B, X. There's one that says X goes to B, X. And there's one that says X goes to A. Okay. Well, let's see how we can convert this regular grammar into an NFA or DFA. Okay, well, we need a certain finite automaton. So what's that finite automaton going to look like? I think we're gonna make a DFA in this case, and it's going to consist of some kind of alphabet and some, oh boy, some set of states. I'll call that S sub DFA or something like that. This is terrible notation. And we're going to have a transition function, and we're going to have a start state, and we're going to have a set of accept states. Okay, so if I can explain to you how to convert this grammar into this DFA, then I will have done my job. Okay, well, first of all, of course, I think we just want to set the alphabet for our finite states machine should be the alphabet of our regular grammar minus lambda. I don't want this null character. I do want this null character to be considered a terminal symbol in my regular grammar, but it certainly should not be a character of my alphabet. So I think that's pretty clear. And then set. Yeah, here I guess I used, for clarity, I used like some cursive S. Okay, which I somehow forgot how to do. Whew. Yeah. Is that how you do an S? Oh my god, I haven't done an S. I haven't done a cursive S in so long. That seems wrong. So, wow. Okay, I'll just keep it like that. Okay, so whew, I used to use cursive all the time. It's like this? Yeah, wow. So, okay, sure. Okay, so what is this? What is this set of states, of course? Well, okay, duh. Big surprise, it's going to be it's going to include at least one of every one of these non-terminals. Okay, well actually, let's just go. I will explain. This is just what Gauss does as well. I will explain how to create the states of this machine sort of as we go. And I think this example is like already kind of a little bit interesting. So, all right, let's begin. I need a start state, and the start state of my DFA is yeah. Okay. Let's just start. So here's my start state. So what can I say about this start state? Well, it should be it should be the same as the start symbol of my regular grammar. In other words, if I'm being more careful, I probably need to rewrite these notes more carefully, but in other words, there's a start symbol in the regular grammar, and there's going to be, for every non-terminal symbol of the regular grammar, there is going to be a corresponding symbol, there's going to be a corresponding state, rather. So we have at least, maybe I'll just do this, we're going to have at least one state for each non-terminal symbol, but possibly plus more. Okay, so I'll just call this, now that I have this cursive S, there's no possibility for confusion, so I'll just call this S, the start state. Okay, and now, well, I'll just make another one. Here's X over here as well. So I'll just create the states. In other words, what I've done is to create states corresponding to each one of the non-terminal symbols. Okay, now, let's do something else. Let's start taking a look at these rules. Well, here there's a rule that says that S goes to lambda. And in fact, whenever there is a rule that says that a state, that a non-terminal can be replaced with lambda, then that's another way of saying that from that state we should accept. So I shall make my state S an accept state in corresponding with that. Also, since this state S is the start symbol, then the state corresponding with that start symbol is the start state. So I've just outlined, I'm just going to do this whole thing verbally. I've just outlined how to define the set of states, or at least some of them. I've outlined what the start state should be, and I've outlined how to deal with rules of the form S goes to lambda. Okay, and now we see that there's already sort of a little problem.
5 minutes, my mom's looking at 5 minutes.
Okay, we've seen that there's already a little problem, which is that I need this rule of the form SABX. But okay, according to Gauss's definition of regular grammar, this is a regular grammar, that we're allowed to have rules of this form. But now you sort of see maybe one of the theoretical drawbacks of allowing yourself to have more than one terminal symbol on the right-hand side of a production rule in a regular grammar, is that now I need to when I convert this regular grammar into a DFA, I need to like take a pit stop because I can only process one character at a time. Okay, so I'm going to create a new, and here's why it's not quite true that there is exactly one. It's true that for every non-terminal symbol there's a state, but there are also other states. I need to create a new symbol called, like, I don't know, S prime, I'm just making this up. And anytime you have, in one of your production rules of your regular grammar, a string of characters like right after each other like this, then you need to sort of process those one at a time. So I create this new symbol, I create this new state which represents sort of the halfway point of generating the string ABX or something like that from S. So from here I should read an A, and from here I should read a B, and then go to X. Okay, I think this is very clear. What else? Well, from X there's a rule that says generate a B and go back to non-terminal X. So that just kind of writes itself. And now finally, from X I'm supposed to be able to write an A and sort of then terminate. Okay, well if I'm going to write an A and then terminate, I need to terminate somewhere. So I create some new state, F, and this new state F is just where I'm supposed to go after reading that A. I can go to this accept state. And once we're there, we accept. Okay, this is sort of okay as is, in the sense that this machine does everything it's supposed to do. And I sort of won't say any more about this because I think we've talked this out now pretty thoroughly. You should be convinced, at least for this example, that the only strings that this machine will accept are the strings that I can generate from this grammar and vice versa. Now here, we're just a couple of tiny steps away from this being, in fact, a deterministic finite automaton. If I create a new state, Gauss calls it black hole, we've been calling it garbage state. If I create some new garbage state, oh, you don't have to do this. So if you stopped right now, this is an NFA. But perhaps you think that the algorithm should convert a regular grammar to a DFA. Well, you can do that. Because from the start state, if a B is red, we go to the black hole. And from here, if an A is red, we go to the black hole. And from here, if a B is red, we go to the black hole. And from F, if an A or a B is red, we go to the black hole. And then finally, once you're in the black hole, you never leave again. So in other words, I can sort of patch the non-determinacy,